Hello and welcome to another video in this series of algorithmic art tutorials. Today we're going to be looking at quite an interesting topic called reaction diffusion and the patterns that emerge from that kind of mechanism. One of the things that is interesting about this algorithm is that it produces patterns which we sort of see in nature, and there might be a connection between what happens in nature to generate those patterns and the simplified kind of version that we're going to implement. So in nature you sometimes see these kinds of almost like a maze or a kind of growth type patterns. So this is a reptile skin. You see sort of zebra patterns as well. You have fish with these kinds of designs. You have kind of snails and kind of hard-shelled kind of animals as well, and even plant forms as well. So when I first look at these kinds of patterns, I sort of think this is some kind of algae or kind of fungal growth, but actually we also see them in mammals as well as reptiles. This is just a Google search for reaction diffusion patterns. There's leopard skin as well. So like a lot of good algorithmic art, some of the inspiration is found in nature, and sometimes there are theories that say that the mechanism that causes these patterns in nature is the simple method that we're going to be implementing. I don't know if that's true or not, but it's quite likely actually, given the idea is that it's an interaction between kind of competing, I guess, chemicals or kind of other biological agents. So have a search yourself on your favorite internet search engine for reaction diffusion patterns, and you'll find kind of interesting kind of designs. Here's some that I'm just kind of looking at. There's some as well. Some of them are a little bit more geometric than others. Here's the one with the hard shells. So yeah, it's quite interesting. So let's kind of crack on and talk a little bit about the allegedly simple mechanism that creates these patterns. So one of the web pages that a lot of people refer to, I'll include the link in the description, is this page, and there's a reason why everyone refers to it, because it's actually a very clear, simple explanation of what's happening. I won't read it to you because you can read that yourself, but I will try and kind of talk through my interpretation of it and hopefully make it even more accessible. But it is actually surprisingly readable and a simple kind of explanation of what's happening. So let's try and do our own one. So imagine we have two kinds of species. They could be molecules, chemical compounds. They could be kind of predator and prey in nature. I don't know, rabbits and carrots, or mice and falcons perhaps, or owls, where one kind of eats the other. Let's say we've got this some chemical here. As I say, it doesn't have to be a chemical, but the mechanism kind of works when we speak about chemicals or kind of animal predators and prey. So we've got these green things here, and let's say these are the predators, and the prey are coloured in red here, and they're kind of dotted around. So you can see in this environment we've got a mixture of red and green, predator and prey. So in the animal analogy, what will happen is that two predators will eat a prey, not one but two. So imagine the prey is quite tough, so it takes two to gang up on it and eat it. So there's another example here where they're close enough to eat it. Here's another example. Is there another one? Here it is. This one is far away. This one's far away. If we did have one here, that still wouldn't be enough, because we need two of the green ones to make a red, to eat the red. And when they've eaten the red, they produce another one themselves. So from a chemical perspective, we say 2 greens plus a red becomes 3 greens. So that's the kind of chemical reaction, as it were. And notice here then we have 2 greens here and 3 greens, so we're actually increasing the population of the greens. And in terms of 1 red and now 0 red, so that's kind of depleting the population. And that's a really important idea here, that this mechanism increases the population of one of the species but decreases the other one. So over time, if these are all kind of jiggling around and moving around, you can imagine that over time the red blobs will vanish, because eventually they'll get eaten up and converted, as it were, into green blobs. So that's kind of boring. If we started off with a simulation where we randomly put red and green blobs in a kind of an environment and let them jiggle around, and then applied this idea that if 2 greens and a red are close enough, then suddenly the red becomes a green, then over time they'll all become green. If there's a variation on that, it might be that actually there might still be some reds hanging around because the population is so not dense that they never actually hit a green. But not that interesting. Let's add another dynamic to this. So I'll just draw a box around here and say that's our environment, and we're going to kind of make things a little bit more interesting. And what we're going to do is we're going to feed red blobs at a given rate, at a rate f. So even though they're being depleted, we are going to be feeding them in. And what's more, because the population of the green blobs keeps going up, we're actually going to have a kill rate, so that we start kind of culling them, as it were, at a given rate. So you can imagine that depending on the rates, we could have a big influx of reds and it might overwhelm the greens. We might have, if the kill rate is too low, then we'll just have an overpopulation of greens. If the kill rate is really high for greens, then there might not be enough to kind of convert the reds into greens, and there'll be overpopulated reds. Or you can imagine there's a balance where, we are producing and causing this reaction, but picking just the right F and K, the feed and kill rate, then we kind of maybe reach a steady state perhaps. What's surprising is that this simple mechanism that I've just described, even though you'll see it described in kind of mathematical language like this kind of thing here, this idea is all there is actually to a simple reaction diffusion mechanism. And we wouldn't be doing this video if we didn't, if it produced boring patterns. It produces interesting patterns as well. So we'll see that. So that's the basic idea. Now I'm sure there are more interesting variations on this, but fundamentally, all the variations will have this core idea of competing species or kind of animals or chemicals, and then a mechanism for kind of depleting one and growing another, and then feeding and a kill rate to kind of maybe adjust or compensate for perhaps the conversion. So that's what happens. In terms of implementing this, we'll with computers we naturally work in grids, so we'll try and think about how to do this in a grid. So if I have a grid, we'll have a bigger grid, but let's just say we've got 1, 2, 3, 4 by 1, 2, 3. So 4 pixels by 4 pixels. So not very massive. And what we'll do to simplify the model is we'll imagine that each of these locations has a concentration of competing agents, red and greens. So if I've got a high concentration of reds, like this one, then my concentration, say it goes from 0 to 1, this might be 0.9, and the green blobs, there's maybe only 2 there, let's say that's got 0.1, so that's a low concentration. So we're not having to model individual molecules or atoms or animals, we're going to be modeling concentrations. This one might be more balanced, sort of 50-50, so 0.5, 0.5. This one might be entirely 1.0 and no greens. What we talked about earlier was the reaction. The diffusion part of this says that the higher concentration areas diffuse into the lower concentration areas. So this has got a high concentration of red, and it will move into neighbouring regions or cells or grid points. If I've got a high concentration of, say, greens here, and I'll actually have a high concentration here as well, because it illustrates an important point, there will be a net flow from here to here, because that's really high. Let's say 0.9, and this is 0.2. There's a big difference there, so there's a kind of a gradient in concentration. So we'll have a net movement from this to this to try and equalize it. These two, and this one might be 0.9 as well, so they're equal. So there isn't a gradient or a difference, so there won't be any kind of net movement from one to the other. So you can see the movement happens a bit like temperature. It moves, heat moves from areas where there's more energy to areas where there's less. So the hot things will reach the cooler things. Things don't really move out of low concentration areas, low density areas, but things move into them, unless of course there's even lower concentration next door. So this might be 0.1 in the red, and this one might be just 0. So there's still a small flow there. So that's the idea of diffusion. So we have a reaction, which we just described, and then on top of that we have this idea of diffusion to try and equalize concentrations. So you can see again there's competing dynamics here. So the reaction will try and create more greens from reds. There's a feed and kill rate which can affect that as well. And then on top of that we have this idea of high concentration areas seeping into low concentration areas for both the red and the green. So that's all the mechanisms at play. We'll talk a little bit about how we model that concentration, what the next the next iteration of, if we're modeling it over time, what the next version of this grid looks like. And there's a nice mathematical kind of method for doing that, which makes computation kind of with grids and arrays kind of easier. So let's start coding, and what I'll do is I'll talk through the code. So rather than just presenting the code to you, I'm going to type it and kind of explain it as I go along. And then I'll jump back to drawing more pictures when we get to the bit about concentrations and modeling the diffusion. So let's do that. Let's create a new Python notebook. I'm using kind of the Colab one in the cloud, but you can use Python locally. And I'm going to start pretty much like most people by importing some common libraries. So numpy I'm going to use because it gives me arrays. I'm going to import random because I'm going to randomly populate those cells with random concentrations of A and B, red and green, rabbits and carrots. We'll come back to maybe adding more to this later. We might add more, say the drawing library, so matplotlib, but we'll leave that for now. So that's the importing. Let's just check it runs without any error. The first startup in the cloud is always a little bit slow, but once the machine's up and running, then it's a little bit quicker. So that's great. Let's think about some of those parameters like feed and kill. So I'm going to have a parameters section. So let's say I've got a feed rate, and I could pick any random ones, but I'm going to cheat a little bit and pick some that are known to produce kind of interesting patterns, because you can imagine not all of them do. So if I start off with, say, for 0.0545 and a kill rate of 0.062. Yes, they are deliberately chosen. We'll talk later about the space of parameters and which parameter combinations produce interesting patterns and which don't. You can imagine if my kill rate is really high and I've got no feed rate, then I'm just going to kill I might kill all the kind of the predators, for example. Or if I've got a really high feed rate for the prey, for the red blobs, and no kill rate, perhaps then that can overwhelm the reaction and I have an overpopulation. So you can see there's a balance to be found. That's probably enough for now. Let's now what are we going to do? Let me think. Let's set up the grid. So if I say I've got a grid size n by n, and let's say n equals, I don't know, 1 to 8, just to start with, and I'm going to have 2 arrays, one to model the concentration of the predators and one for the prey. I'll call them A and B from now on. So in terms of this picture here, this is going to be B for prey, B for predators, A for prey. So A and B. So A, we're going to create a numpy array, and we'll start off with a concentration of 1, ones, so not 0, numpy.ones, n by n array. And let's see what that looks like if I just print that out. Oops, I missed out some brackets there. So that's n by n. There, so that's 1 by 1. If I make that, say, 4 by 4, you'll be able to see what that does. So that's a 4 by 4 array with ones. So we want 1 to 8. And we want one with B as well. So numpy dot, and this time we'll initiate it with zeros, and that's n by n. Now you might be thinking, why do we want 2 arrays, A and B? Well, there's different ways of implementing this, and you could have one grid, one array, n by n, and then within the elements of which have 2 components, A and B, A and B, the 2 concentrations. But that is a possibility, and if I was going to do this in, say, JavaScript or something like that, that might be what I would have done. But we are going to take advantage of NumPy's ability to work with whole arrays really quickly, so it's very computationally efficient, one of the advantages of NumPy. So to do that, it's easier if the A's and B's are actually separate arrays. That means we can kind of operate on them, an array at a time, or enough, it gives the illusion that it does, and there are optimizations that happen under the hood. So that's the reason for 2. And we're gonna enforce the type of the elements to be floating point, float 64. You can just say float or float 64. So we're not going to risk it kind of accidentally becoming int or something like that. We're being quite explicit that it's going to be a float 64. So I've made an error somewhere. Here's a comma. Great. So now I've got my arrays. I'm going to now, so let's just draw a picture of what we've done. So A is the prey and B is the predator, and we've said the kind of 2 B's plus an A becomes 3 B's. That's the kind of reaction. And to start with, we've said we're going to have a concentration of all, kind of a full 1.0 concentration in each grid of A, so that's 1.0 in every whereas here we started off with 0, but we're going to randomly pick some and give it a concentration of 1. So we'll maybe pick that randomly, maybe that one randomly, so that's 1.0, so that's a full concentration. So we're not going for like half or a third or any other fraction, we are just going zeros and ones, just to keep it simple. But it won't be all of them, it'll be just some of them. So let's do that. So we're going to add random ones to B. So as the concentration becomes 1 in some of the cells. So we could use a loop to go over each element, following the X and Y, but that's quite inefficient, so I'm going to try and do this in a numpy way. So I'm going to try and create a vectorized function which numpy can apply kind of all in one go, rather than us writing 2 loops, an inner loop and an outer loop, to kind of visit each element of those grids and then do something. So let's write a function, let's call it initialize B, and it will take a parameter X, and we're going to say it returns, so we're going to say, well, let's think about it, it's going to return, if there's a probability, let's call that just star there, if the probability succeeds, like if the chance coin flips the right way, then we're going to say we're going to return 1, so the element will have a concentration of 1, else we're going to return 0. So we're going to numpy will visit each element of an array, of the B array, and it'll throw a coin, which we haven't defined yet, and depending on the outcome of the coin, it'll fill that element with 1, otherwise 0. So we don't want to overpopulate it, so we'll say if random dot random, so that's between 0 and 1, is less than 0.05, so 5% chance. So let me just put a comment in there. So chance of B equals 1 is 5%, or 0.05. So quite a small chance, but still there. So 5 in every 100 may be flipped to have a concentration of 1. So that's so there will be a few of these elements of the B array, the predators, which will have a concentration of 1, but most will be empty. So that's the function which we now need to vectorize, and we can, let's say, vectorize for numpy, and then we say initialize that one. Let's call that a different name. Let's call it vectorize function equals numpy dot vectorize. The Americans use the Z spelling, and initialize B. So that will take our function and turn it into a vectorized function. Now, just a little caveat there, these aren't always faster. If you look at the documentation, they do run loops. If you really want to have functions that do operate kind of at a per array level, then you have to do it a different way. But this is just it's convenience, I guess. It allows us not to write loops. It allows us to say, write in the idiomatic style of numpy, operating on whole arrays at a time, so we can apply this function to an array and it will apply to every element rather than us having to loop over it. So we probably don't gain much in speed, but we kind of have nicer code. So that's the vectorize function, and we should be able to initialize it. So let me make a small one, just to let's say 5, just to kind of see what it looks like before we apply it. So this should be zeros. So this is the B array initialized to 0, which was there. If I did A, that should all be 1s. Yep. And now I'm going to update B. I'm going to rewrite it as it were. And so I'm going to say initialize with the vectorized version. Initialize B VF. And that should give me a new version of B with some of the zeros turned into 1s. Let's try and print that out. That might not happen with such a small array. Or am I misspelling it? Yeah, I misspelled it, so let me get this spelling right. Initialize. So yeah, you can see here that it's mostly zeros, but there is one element that's become a 1. So that was by 5% chance. If I run it again, there was none, because 5% is quite low. Run it again. None. Run it again. Oh, there's 2 this time. But you can see overall it's quite a low chance. Great. So that was the beauty of vectorizing it. It allows us to say that vectorize function applies to a whole numpy array, and then we get an output. I didn't need to write loops to iterate over each cell or each element of the array. Great, so now we've got ourselves initialized. Let me go back to 128, which is much larger. Now what do we want to do? Let's visualize what that function looks like. So if I say I need to import matplotlib to start showing these things, import matplotlib dot, is it plt? I can't remember now, was it? I can remember these things, I always have to look them up. Matplotlib.pyplot. God, I wish they'd make this into something that's 21st century, but it works. So that's a standard pattern, I guess, that's burned into our brains. So if I rerun that, and now I can say figure equals, I can create a figure, plt.figure, that creates a figure, and then I'm going to create an image, plt.imshow, which is what we use to show an array of numbers. Let's say B just now, without any further options. And I do want to close it. Yep. plt.show, just to close that. Let's see what that looks like. Yeah, there you go. So you can see that it's mostly zeros and some 1s, and that's kind of what you'd expect, kind of a spattering of predators. If I did it with the A array, it should all be 1s, so it won't be interesting at all. Let me avoid that interpolation that it does. Interpol, this is just a kind of visual effect. Interpolation to make it none, so it doesn't have that kind of smoothing. There you go, actual little squares. And I'm going to choose a color map, and you can choose your own, whichever one you want. This is the one I'm using, and I'm going to tell it the minimum and maximum. vmin is 0, so it kind of, if I tell it what the minimum and maximum value should be, then it can color accordingly. What I might also do is add a color bar. So fig.colorbar, is that American spelling again? Color bar, and that's based on the image. There you go. So the greens which are harder to see now, are values 1. The deep purples are value 0. And that will be kind of useful for us later when we animate and see movement. So that's kind of the initial state. What we want to do is actually run these as generations, so let the reaction start happening, and update this kind of image as an animation, so we can see what's happening to kind of the population of bee, the predators. We could plot A, we could plot B, we could plot some combination of both, and you can do that yourselves. To keep things simple, I'm just going to do B, the predator. So how do we do that? Well, the way we do that is we actually create an animation. So I'm going to have to import some extra libraries. Let's see what they are. So import matplotlib.animation, and I'll talk a little bit about how that works. I'm also going to have to update a parameter, matplotlib.rc parameters. So this is kind of ancient, isn't it? Animation.embed limit. And this is because when this was designed, the animations were quite small, like a few frames, for showing, say, the evolution of a function or something. Curves plotted on a chart, maybe moving, but certainly not sort of hundreds of frames or even thousands. So we're going to up the limit to a really big value. So that should avoid kind of errors there. I'm also going to import the ability to show animations in the this Python notebook. So from ipython.display, I'm going to import HTML so you can show HTML and render that, which in our case will be an animation. So let's rerun that. So let's update our code. So for the HTML animation, we're going to create an animation object from matplotlib.animation, and I explained how this works. We use something called a function animation, and what this will do is it will call a function that we define, and that function will do whatever it needs to do, calculations or generating up the next generation of these predators and prey, updating the grids A and B with new concentrations. It will do that and then plot the result, and it will do that for as many frames as we want. So that's how it works. So we have to tell it which function we're going to be calling, but first it needs to know which figure it's going to operate on. We'll call our function update. We'll run it for, say, 300 frames, 300, and the interval is how long each frame is displayed for. I think it's in milliseconds. Great. So update doesn't exist, and then to display that we use anim to convert the animation to a kind of JavaScript HTML thing, which will play. But we have to first write our update function. So we can write a null one first. Let's write it up here. So we'll say the animate function. So def update, it takes a parameter which is the frame number. We're not going to use it, but let's just return. So nothing happens, but we'll just test that it works. So if I run this, what do I get? Just testing the code works without breaking. So it's running that for 300. It's calling the update function 300 times, once for each frame. So it's going to take a while. Let it run. Maybe I should have done just 20 frames or 10 frames. So here you can see now it's not just a plot, it's got a kind of a video play button. So if I play that, it's moving, but there's no movement in the image because we haven't updated anything, but at least we've got the kind of the mechanism working. Right, so now let's start thinking about the core of this update function, because that's where we're going to have to do the diffusion reaction model to generate the new updated concentrations for each new frame. So that's where the action is. So we're going to probably have to refer back to the model. So we talked earlier how, you know, there's this reaction that happens, but there's also kind of a feeding and a kill rate, and then on top of that we've got areas of high concentration seeping into areas of low concentration, and that is all kind of modeled mathematically. And when you look online, you'll see different variations of this, some more sophisticated than others, but the standard one to go for is the one on this page that I'm going to be linking to, and it looks quite scary, but it isn't, and this page actually does break it down. But let's talk through it. So hopefully you can see that. Let me zoom in a little bit there. So hopefully you can see that. So if we take the A array, that's the prey, and similarly for the predators B. And what do? We add something to each. We take the element, each element, each concentration, each cell point, each location, and then we adjust it. And how do we adjust it? Well, we adjust it according to this complicated thing. So let's break that down. We take the current value and then we add something that depends on the diffusion. So this calculates the difference between the current cell we're looking at and its neighbours. And if this cell is more concentrated, there's a higher concentration in this cell of A than its neighbours, then this thing will adjust so that the neighbours will get more and this cell will go down. So it's trying to equalise the concentrations. Where there's high, it'll become low. When there's low, it'll become high, as long as there's a neighbour to feed off. It's moderated by a diffusion rate. So this kind of thing is complicated thing is called a Laplacian, which is done by kind of convolution, which we'll talk about. It's not actually that complicated, so even though this looks complicated, it really isn't. So just put it into plain English. We have something that calculates relative concentrations and tells us whether we need to increase the concentration or lower it in order to equalize with our neighbors. So that's what this bit does, and that's moderated by a diffusion rate, so we kind of don't flip-flop too much. We kind of, if the difference is like 0 and 1, let me draw a picture there. So if I've got 2 grid cells and the concentration here is 1.0, so quite high, and almost nothing in this one, so 0.0, you might say, well, we have to kind of make that 1 and that 0, but if we do that, then that's just flipped it, and the next time we do it, we just flip back, and then we just keep flipping, and that's not really how nature works. So we'll moderate that by a diffusion factor. So if that's say 0.2, 0.1 or some other small number, then some of this will go up and some of this will go down to a lesser, more gradual extent. So that's what that does. So we need to actually create some of these diffusion parameters. So let's say diffusion parameter for A is 0.2. You can play with other factors. I'm just taking one that I know will create some interesting patterns. So interesting that they're not equal, but you can play and see what happens when they are equal, when they're high, when they're low. If they're too high, then what happens is the patterns oscillate rather than kind of grow organically. Right. Next we are looking at this term, which encapsulates the idea of that chemical reaction. So because the concentrations are 0 to 1, they're effectively probabilities. So the probability of two B elements, two B molecules meeting an A molecule is AB squared, because they're already 0 to 1 probabilities. So you can imagine if B is higher and A is higher, then that's more likely that that collision of two B's in the A will happen. If any of A and B or both are low, then the probability goes down. But because there has to be two B's, that's why it's a B squared. So the probability of independent events, so A, probability of A times the probability of B times the probability of another B, A times B times B, AB squared. Now, when that happens, an A is converted to a B, so that's why there's a minus. It reduces that, and the population of the B goes up, which is why there's a plus. So that's why there's that symmetry there. And then we have terms related to the feed and kill rate. So we have concentration of A. If we 1 minus that, then we kind of invert it. So if the concentration of A is really high, 1 minus that is a low number, and then we're going to multiply it by the feed rate. So the feed rate is almost proportionate actually to what's kind of already in there. That's just the standard. That's kind of standard formula that people use. You're more than welcome to play with other variations and see if you can have a different way of feeding and killing A's and B's. Here the kill factor and the feed factor are kind of added together and multiplied by B. So that's again the standard one that everyone uses, but again you're more than welcome to kind of play with other variations. But the core idea is those three things. We have a diffusion, which is trying to equalize concentrations. We have a reaction where A and two B's meet and either decrease or increase the population, decrease A, increase B. And then we have a feed and a kill rate, and you can play with your own functions that do that, but this is the one that is quite commonly used out there. This one uses a delta t, multiplying it by kind of a time step, but for us we'll just have delta t is 1, time step is 1, so we won't need to kind of multiply that. Just keep our equation simple. So let's kind of implement that in our update function. So we have created A's and B's at the top, and we need to access them from inside this function. So we need to kind of say that we are accessing global variables. Otherwise it doesn't work, because otherwise variables created inside a function just stay there. They're not referring to the one outside. So this says we intentionally are wanting to access and update global variables. So let's do some pre-calculations. Pre-calculations. So if we're using a quantity like that AB squared twice, might as well just calculate it once. So let's call that AB2 is A times B times B, and that's an element in NumPy. That's an element-wise multiplication. So it's not a matrix multiplication, it's multiplying each of the corresponding values in the cells. So the top left times the top left times the top left, and so on. And this is one of the nice things about NumPy. Instead of looping over all the arrays, all the kind of axes, I can just write a times b times b, and it creates a new array where each element is the corresponding ones, with that kind of multiplication happening. So that's kind of nice. If I was doing this in JavaScript, it would have been really painful to try and write functions which create arrays and they're not even native to JavaScript, and then having lots of ugly loops to kind of write it. It just makes the code really heavy. Having said that, arrays aren't native to Python either. This is a numpy library thing, and core Python doesn't have multi-dimensional arrays. But I guess numpy is pretty much considered part of core Python pretty much now. So that's nice. So that's got we've got the AB squared. Let's also work out the diffusion. Now this is where some of the magic happens, and I will kind of draw pictures to explain it. But what I'll do is I'll write out how we. Actually, let me start with drawing. So if I've got a grid, let's just call it a 3x3, and if this has got a really high concentration, in the next iteration, what do I want? I want this one to go down, and I want these to go up a little bit, and maybe the ones on the other end a little bit as well. Ideally some kind of circular distribution, but I definitely want the middle one to go down and these to go up, and the ones that are up, down, left, right will go up a little bit more than the actual corners. So I want something like 0 0 0 0 1 0 0 0 0. I want that to become something like, I don't know, 0.1 0.2 0.1 0.2 0.2, let's say -1, 0.1, make it symmetrical, 0.1 0.2. So you can see what's happening here is, if there's a high concentration, it'll be knocked down. If there's nothing, we're adding, and these are higher than the actual corners because the circle touches the left, right, up, down more than it does the corners. So that's the kind of operation we want. Now, how do we do that? Well, some people implement this by kind of scanning over the array elements, and just doing that, adding and multiplying with this kind of mask or filter, as it were. But this is a common thing actually in signal processing and kind of manipulating images and so on, filtering images. So NumPy actually, and the scientific libraries, SciPy, give us this. It's a very common thing to do, and it's called a convolution. So we define what this this kind of filter is going to be, and then apply it. So if this was 0, then we wouldn't need to change it. If this was high, then it would be kind of multiplied by -1, and then we kind of apply that over the image to get a new kind of a convolution array, as it were, which has these values which are telling us to what extent these values need to go up and down. So it's the up and downs, if you want to call it in simple plain English. This array that comes out of doing this is the up and downs, which we then apply to this array to give us that one. Does that make sense? We'll kind of talk about that. Actually, let's illustrate it. So what I've done is created just a simple kind of notebook, just illustrating that. So I'm importing SciPy. I'll share the link to this as well. This isn't the main code. This is just a side bit of code to illustrate that kind of up and down array. So I'm importing NumPy, the signal part of the SciPy libraries, and the matplotlib just to show. Now that filter is called a kernel, and here you can see the middle of this 3x3 kernel is -1. So it's saying that if there's a high concentration of the location I'm looking at, I want it to go down, and I want to displace it outwards. So 0.2, 0.2, 0.2, 0.2, that's up, down, left, right, and then 0.05, a smaller amount, into the corners. So that's creating an array. That's what it looks like. I could actually look at that if should I plot it? Let's create a new bit of code. So I wonder if this works. ImShow, matplotlib ImShow, matplotlib, this may not work. Oh, it's PLT, isn't it? There, it's just rough and ready code. So you can see the middle is very negative, and then the up, down, left, right has small positive values, and then very much smaller values in the corners. So that's the kernel, and we're going to be applying this kind of filter to every location of the environment, the A and B arrays, and it will tell us to what extent we need to shift values away from the thing that we're looking at. Let's remove that for now. So here's an environment, a small one, 5 by 5, and it's got a 1 in the middle, and we would expect that to be kind of once we apply the convolution, we expect it to the up and down the change array to try and shift away that central 1 into its neighbors, and we use the convolve function. So SciPy signal convolve 2D convolution we apply it to the environment, the T array here, the kernel, which is that little filter that we've defined. The modes, there's different ways of kind of applying a convolution to an array, and you can end up with different sizes coming out. We want to do this so that the output array is the same size as the input array, and you can imagine at the edges we might have to do something a bit funny. Some people ignore the edges and work that way, but then the filter is only partially applied. Others will extend, imaginary extension of the array, and have zeros or ones. What we'll do is just wrap around, so going off the edge of one array, you just pick off the values at the other end of the array. You can experiment with things like that yourself, but it's a fairly standard approach here. So if we apply that, you can see that the 1, we've knocked it down to -1. That's the kind of the change that's suggested to try and equalize the concentrations, and then 0.2 and 0.05. So it's trying to move the high concentration into the neighboring cells. So let's try and plot those. This is a bit of code that just plots the two together. So this was the original array with a high concentration in the middle, and this is the convolution array after the convolution has been applied. And you can see there's 0 here, and it's, the neighbors have kind of taken up some of the concentration from that, so it's moved out into its neighbors, and that's kind of what we want. So that's the idea there. It might be easier to think of this in one dimension. So if I've got one dimension, I've got 0, 0, 1, 0, 0, so it's just a line with a 1 in the middle, and we can convolve it, and you can see that again the middle has been reduced, to -0.6. That's the change that's recommended to try and equalize the concentrations, and the neighbors, 0 will go up to 0.3, and the furthest 0 will stay 0 because the kernel isn't that big. And if we visualize that, you can see here's the input, so 0, 0, 1, 0, 0, and in order to equalize the concentration, we want to make that 0, and then, or reduce it, actually this is not showing negative numbers, and then move the concentration out into its neighbors. So that's what that does. I'll share a link to this example notebook if you want to have a look, and just play with this convolve 2D function. So back to our code. So we want to work out what the that kind of change matrix, the up-down matrix, looks like. So SciPy dot signal. That's what we imported. Did we import it? Oh, I didn't do that, did I? So let's do that. So import SciPy dot signal, and then we're gonna use the convolution 2D, and the first parameter is the matrix, the environment we're going to apply it to. So we're thinking about A at the moment. We're applying the kernel, and ours is the one that pushes concentration out to its neighbours. It's this one here. Did we write it? Oh, we didn't actually write it. So I should do that, shouldn't I? I should actually write this kernel. I'll do it here. It's a new code, kernel, and convolution kernel, and we'll say kernel equals numpy dot array. So we'll try and write it on a multiple lines. So it's going to be 0.05, 0.2, 0.05, and it's a 3 by 3 one. So the next one is going to be, I'll just put the brackets in. So the bottom and top lines are going to be the same, so I'll just copy and paste those. And the middle one, the outside is going to be 0.2 minus 1.0, 0.2. And let's print it out just to make sure. Let's also add the D type just to avoid any accidental casting to integers or anything else that might happen. So there you go, that's the kernel. So just what we've shown in the other notebook. So -1 in the middle, and then shifting out to the neighbours, with the vertical and horizontal taking more than the diagonals. So that's the kernel we're going to apply to the array of prey, and that should work, but we can kind of configure how it's applied a little bit more. So we said we're going to have the output array the same size as the input array, and we're going to say the boundary, we're going to wrap around the boundary equals wrap. So that should give us that. That's kind of what we experimented in the other example notebook, and we do the same for B. Now, just an important point here, this isn't actually the next generation of A and B. This is the array that has the recommendations for how you change the up and downs, the deltas, the change, to that array to try and equalize the concentrations. But as you know, we need to do more. We need to moderate it with a diffusion factor. We need to think about the reaction, the AB squared probability, and the kill rate as well, and the feed rate. So this isn't the next generation, but it's almost there. So now we're going to say new arrays. Let me write a comment here as well. So the comment here is difference arrays to equalize concentration. And the new arrays are going to be A equals A plus, and we can just say A plus equals something something something, and the same with B plus equals something something something. And this is where we refer to that famous equation again, and the first bit is the diffusion rate times that array we calculated. So dA times dA, that's that one. Put brackets around that just to make it easier to read. And then we had minus A times B squared, which is the reaction, the probability of two B's and an A. And remember, we pre-calculated that up here. That's up there. So it's minus AB squared. And then we implement the other bit, which was the feed rate times 1 minus A. And similar here, we have diffusion rate of B, which moderates it, times dB, which is the actual array. And then we're adding AB squared, because the population of B goes up if A and 2B's meet. And then we have do we have a plus or a minus? Let me have a look. Should be a minus, shouldn't it? Yeah, it's a minus. So minus, and we have a kill plus feed rate added together times B. And this simple bit of Python code, almost simple, is this scary looking equation. And as we said, most of the work has been done up here, and the magic kind of happens with this convolution. So now we've updated the arrays. Great, that is actually now just 3 or 4, 4 or 5 lines of code, and we've implemented that diffusion reaction equation. Amazing. Before we finish, we need to update the plot. So we need to it doesn't automatically do that, so we need to update the plot, the image array in the plot. And the way we do that is im, which exists, dot set. We're setting data, set data with B. So we're only plotting B, remember, we're only visualizing B. So that's that function. And let me just try this now with just say 10 frames. So what I'll do is I'll create a new fresh grid. Got the update function, and now we're going to create an animation with 10 frames. And SciPy is not defined. Or did I not import it? Try that again. Another spelling mistake. Did I not run the parameters? I'll try again. Still an error somewhere. Float 64. Should have been a float 64. Ah, okay. So 1.0 return 0.0. Yeah, I knew there's a reason. We had to be careful. So returning 1 and 0 made them into integers. So let's do that again. So this looks like it's now going to work for 10 frames. Yep. This is plotting both, so I'm going to do a little bit of matplot magic again to avoid that. So matplotlib, and it's called notebook. So what this does, it allows us to do the animations without having that other thing being plotted. So let's run that again. Great, so just the animation. And if we click run, yep, so once, so that works. To avoid that kind of repeating again and again, I'm going to write repeat equal false. So it'll only go from start to finish. Now if I run this again, it's actually going to continue the further evolution, so we're going to lose a start, but that's okay, we're just experimenting. So we run that, and we can go right to the start, and we can go backwards and forwards. So you can see that's happening. So what's happening here is we are losing the greens. So we are losing the concentrations of the predators B, because they were green colours, as in near concentration 1, and they're being diffused out, and so they're going into the neighbouring cells, but they're not yet diffusing beyond too far. That's fine. So at least that's working. We've got the animation working now. We've got generations being created. Let's see what happens if we run this for 100 or even 300. Oops, what was that before? What was that? 50 as intervals. Let's run this for 300 frames, and I'm gonna reset the grid. So this will take a few seconds, but if you think about it, it's doing quite a lot of work. So 300 times it's kind of doing the calculation to work out what the next grids, the arrays A and B, should be based on all that stuff around diffusion of concentrations, the reaction, the kill rate and the feed rate. So it's quite a lot of work that's kind of doing. Right, so this should be 300 frames starting from scratch. So let's have a look at what it looks like as it evolves. Oh, that's interesting. And we see some interesting patterns emerge. So one might have thought that you might get a kind of a boring equilibrium, a kind of a simple soup, but actually we have some structure emerging. So isn't that interesting? Now that is a reaction diffusion pattern. So the core idea is that with that relatively simple, innocent looking model with diffusion of concentration away from high concentration areas, with a reaction mechanism, 2 Bs and an A become 3 Bs, and a feed and rate mechanism going on as well, you would think that all of that might just turn some structure slowly into a kind of a uniform soup, but it doesn't. It creates a macro scale structure from that micro mechanism, and if you vary the feed and kill rate, you get different kinds of patterns emerging. So this is really interesting, and you can try other feed and kill rates. And what I will do in the notebook that I share, I will just put some in there which are commented out, which I know produce interesting patterns. So I've called this one worms pattern. A mitosis pattern is similar to where cells split into 2, and then those will probably split into 4 and so on. So that's the process of cell division. There's kind of the coral growth, which is what we looked at. There's others that produce big blobs, swirls. Let's look at the mitosis one and comment out the other one just as an example. So I'll run that all again. It's taken a while. Right, let's have a look at what this one does. Can we see any mitosis happening, or do we need to run it for a lot longer? So these are the cells, and they should... well, they don't quite divide. Okay, we need to run it for a lot longer. Now before I do, there's almost like a limit almost on how long these animations are, because they're all kind of, the frames are all held in memory. So I'm going to paste some code which actually renders them into a video file rather than as a HTML animation. So you can see I've commented out the previous code. It's very similar, matplotlib animation. I'm going to do 10,000 frames, and this time I'm going to save it as an MP4 video file, and the encoder is ffmpeg. If you're doing this on your own computer, you'll have to have ffmpeg, which is the open source video codec, installed and configured. If you're using Google's Colab, it's all there anyway. This, funny enough, is just creating the name of the file, so that the name of the file tells me what the F, feed and kill factors were. So if I run this all again, and then it'll create a file. This one isn't actually completed yet. We have to wait for the cell to complete, and then you download. If you're doing this in the cloud, you'll have to download that video file, which you do by right-clicking on the dots and download. If you're doing it locally, it'll just be created in your working environment. So that's quite clever for much longer animations. So 10,000 frames now. This works much more reliably. I wonder if I should go and make a cup of tea and then come back. It's interesting to see how long it takes. Actually, that's taking too long, so I'm gonna do a smaller number of frames. Let's do 1,000 frames. So let's run that again. Great, so that's finished. And if we download the video file and if we have a look at it, let's have a play of it. And you can see, although it's just 1,000 iterations, 1,000 frames, hopefully we can see some mitosis happening. And we're watching each of these sort of little cells and see if they divide. Yeah, it's starting to happen, isn't it? Yeah, you can see them there. They're starting to split into two. So that's mitosis. That's actually happened. So this is one I did earlier with 256 by 256 grid, and I think it was 10,000 frames, so it took a lot longer. And you can see the little cells starting to divide. Let me zoom forward in time. There you go. You see, if I go backwards and forwards, you can see that mitosis happening. Here's another one with the worms chosen F and K values, and we'll see what happens there. You can see these kind of string-like structures emerging. So first it almost disappeared and then something comes back. It's kind of slow, but it does grow. It does take a while. I'm going to zoom forward just to save time. You can see what's happened there. I'm deliberately fast forwarding, so I'll call these worms or spaghetti. Now, isn't that interesting? A very different kind of scenario. So this was 256 by 256, and I think it was for, say, 3,000 frames. So it will take a lot longer to calculate, but you know, the video file does pop out. So you should experiment yourself with some of the other values and see what other kinds of structures emerge. Here's another different set of F and K values, and this time we have different kind of patches, blobby patches emerging, so a different kind of structure. Last one I'll show you, because you should experiment yourself, is this one where we see that initial familiar kind of settling down, but then a different kind of travelling pattern emerging. Isn't that interesting? So these swirls kind of grow, but they also disintegrate as well. So let's run that in normal time. It is quite slow, yeah. But yeah, sometimes you end up with travelling patterns as well, like travelling waves and little objects that move around. Some people call them solitons. So that's kind of interesting. Before I finish, it is worth kind of going back to talk a little bit more about the choice of F and K values, which are determining these patterns. That web page has actually quite a good kind of summary of the different kinds of patterns that you might see emerging, and there's almost a map, as it were, of the K kill rate and the feed rate and the kinds of patterns that emerge. So I think this is K across and F up, I think it is, and you can see that if you certain regions of the FK space create certain types of patterns. So if I move in this direction, I'll get more blobby patterns, get disintegrated patterns, get worms, get traveling waves over here. So that's an interesting bit of work to kind of map out what the F and K values do. So I will stop there. I will share the code that we've written and a link to that web page, that useful description. So I'll finish by saying, again, the beauty of algorithmic art, we have a very innocent looking, simple-ish algorithm that creates really interesting structures and patterns, and the core of that idea was diffusion, moving from high concentrations to low concentrations. A reaction, 2 Bs and an A make 3 Bs, kind of consumes an A. The idea of a feed and kill rate, and just that, 3 or 4 simple ideas combined create this really interesting organic structure. So that was really interesting. That was a topic that some people did request, so I hope you enjoy that, and we'll see you again in future for another algorithmic art adventure. See you then. Bye.